So we've been looking at the method of Lagrange multipliers. And once again, you can think of this as an alternative way to maximize or minimize functions on boundary curves. And so the setup is, at least what we've been working on anyway, is we've got some function f of x, y. We call it our objective function. And we're trying to find the maximum or minimum of this. And we've got a constraint curve. And we're trying to find the max or min subject to this constraint. And Lagrange's theorem says that the max or the min are going to come from the solution of the following system. Places where the gradient of f is parallel to the gradient of g. And then, of course, you've got the constraint. Okay. So we've looked at a couple examples of this, at least in 2 dimensions. We've got one more 2-dimensional example to look at today, and then we'll talk about extensions to three variables, and then extensions to more than one constraint. And there's a nice little project to be had if you want to take what we did with Lagrange multipliers and extend it. So we'll talk about that here towards the end of class. So let's take a look at this. This is a classic example. Use the method of Lagrange multipliers to show that among all rectangles of a fixed perimeter, C, the one which maximizes area is a square. And so as I'm seeing here, that C should actually be P for perimeter. So the hint is, suppose the dimensions of the rectangle are x by y. So we can go ahead and look at that. Then you need to maximize A of xy. That's the area. Subject to the constraint, 2x plus 2y is p, where p is some fixed constant. So that's the perimeter. And how do you know what you found is a maximum? So this is another example of where we can use symmetry to predict. Our critical point is going to be where x and y are the same, because this entire system is completely symmetric in terms of x and y. If I switch x and y around, neither of these equations change. Okay. If I think about what's happening geometrically, if I think about 2x plus 2y equals p, once again, p is going to be a positive constant because it represents a perimeter. What I've got is a line with the x and y intercept there. And since we're trying to make a rectangle, x and y are both technically positive. Now we could include x and y being 0. The area at those points would be what then? It would just be 0. So it's not going to... So clearly those would be the minimum things. So there should be some maximum somewhere in between. Okay? And the Lagrange multiplier system that comes out of this is pretty immediate. So we want the gradient of A to be lambda times the gradient of, well, I guess that's our G here. So the A is xy, and our G of xy, well, we could just take that to be 2x plus 2y. And so I got my ax be the partial with respect to x, treating y as a constant. That's going to be lambda gx. And my ay, partial with respect to a treating x as a constant would be x. That's going to be lambda times 2. So we get right off the bat that x and y have to be the same. And then whatever x and y are, lambda is just 2 times that. So if x and y are the same, we immediately get x and y are p over 4, and then lambda would be p over 2. So it falls out pretty quickly. And how would we know that this is a maximum? Well, we can go back to our diagram here. And we have a equals 0 at these points. The only other critical point we would get would be at p over 2, p over 2. That would be p squared over 4. And whatever that is, that's certainly going to be a positive number, so it's bigger than the other two. Okay? So this is it's a pretty simplistic example, but the reason I like to go over it is because this is a nice example to help you think about what that lambda is actually talking about. And we'll talk about this later. So we'll come back and revisit this here in a few minutes. The other reason I like to do it is that this kind of approach can be helpful, like on that one, the shipping problem. The shipping the box problem that's on your take home. You can use an analysis like this. It's one way to do it. There are other approaches to do that shipping problem, but this one might be one. It kind of combines a couple different methods we talked about before. Okay, so that's your classic kind of problem. And once again, the symmetry's here to help us out. All right, so what would happen if we had more than 2 variables? So what if, so once again, for two-dimensional things, you got an objective function, and you got a constraint, the critical points, you're looking where the gradients are parallel. Okay. If you just look at this equation, you can generalize this equation to however many variables you want. So if you've got 2 variables, great. This would give you 2 equations here, equating each component of the gradients, and then the third equation. So you'd have 3 equations, 3 unknowns. But if you're looking at optimizing a function of 3 variables, that's your objective function, and you've got a constraint that's got 3 variables, you can use the exact same thing, right? You just got the gradients here. You would get an equation for each component of the vector, x, y, and z, and then you'd also get the constraint equation. So that'd be 4 equations and 4 unknowns. And once again, why would that theorem generalize that way? That's the properties of the gradient, right? The gradient is orthogonal to the level surfaces, and that's really what's going on. It's the same proof you would have, you just have one dimension up. So if you go back and look at the proof of Lagrange's theorem, you just tack on that z component to the parameterization and you're done. All right. So what's nice about that is we can revisit some problems here that we've actually seen before. So let's just look at what this is asking us to do here. We're minimizing this function subject to this constraint, and we're asked to interpret geometrically. Okay, so the function we're asked to maximize or minimize is our objective function. And so this represents our constraint. So we've got our f of x, y, z. And to make this a little more calculus friendly, instead of writing it as a square root, we could write this as what power? Yep, the 1/2. And then for our constraint, we've already got this equation written as essentially all the letters on one side equal to a constant. So we can just pick the g to be what? Well, the function g wouldn't be 6. The g of x, y, z is equal to 6. So this represents the level surface. Yeah, good. This represents the level surface of x plus 2y plus 3z. Okay. All right, so now I got to calculate the gradients here. So we're going to look at the partial with respect to x. And match that up to lambda g of x, and then so on and so forth. And once again, if you look at the function f itself, it's completely symmetric in terms of x, y, and z. So once we figure out the fx, we should be able to just permute through the variables to get the rest of those. Welcome in, Derek. All right. So the fx is lambda gx. So we're taking the derivative of something to the 1/2 power. So we're going to get that thing to the minus 1/2 times the derivative of that thing, all with respect to x. So what would fx be? Once we know fx, we'll be able to get the rest of them. So we'd get, well, and then we'd also have that quantity. So you'd get your, whoops, oh no. Yeah, exactly. Yeah, so you take the derivative of x squared plus y squared plus z squared to the minus 1/2 power. You're taking the derivative of something to the minus 1/2, excuse me, positive 1/2. You're going to get 1/2 times that something to the minus 1/2 times the derivative of that something with respect to x. So those are going to zero out. I'll just be left with the 2x. Then I'll just use commutative property and move that factor over there, and the 2's will cancel out. Okay. And then if we want, we can put that denominator in its place like that. So we can get that. So I would have x over the square root of x squared plus y squared plus z squared equals lambda gx. G is just a nice linear function. What's gx? Good, just 1. So that's going to be lambda, 1 lambda. And then I need fy is lambda gy. Now because of the symmetry of f in terms of x, y, and z, if fx is x over this square root, then what's fy going to be? Instead of x, it'd be a what? Yep. Good. A y over that thing. And now this is going to be lambda times gy. Gy is going to be 2. So that's 2 lambda. And then finally we got fz is lambda gz. And so then that's just going to be a z up there. And that's going to be 3 lambda. So we can think of this as being equation 1, equation 2, equation 3, and then equation 4 is always just the constraint equation. X plus 2y plus 3z is 6. All right, so those are our 4 equations we got to work with. And what we're looking for is a solution to that system. So we need to find x, y, z, and lambda that make all these equations true. And so the tools we have at our disposal are substitution and elimination. If you look at equation 1 tells us exactly what lambda is in terms of everything else. So one strategy would be to start with equation 1. That's what lambda is. And sub that into equation 2 and equation 3. All right. So we'll start with equation 1 and sub it in there. So let's see what the new equation 2 would look like. It would look like y over over this square root would be 2 times the x equation 3, z over this would be 3 times lambda, so it would be 3 times that. Okay. Now, before we go multiplying stuff through and canceling things out, I suppose we should address the question, is it 3x? Probably. Hold on. Yes, thank you. 3x, thank you. So before we go too far along here, we should ask ourselves the question, we've produced a denominator here. So before we get too far along, can this denominator ever equal 0? Yeah, this would equal, exactly, this would equal 0 if x, y, and z are all 0. So we have to say, well, can that happen in this situation? So we go back and we look at our constraint. If x, y, and z are all 0, is that going to satisfy our constraint equation? No. So we're cool. So, but we should, anytime a denominator shows up, we should ask that question. So there's no worries here, not on the constraint. So we're good. Okay, so we can go ahead now with reckless abandon and get rid of them. Because if you look at what happens here, right, this square root's going to do what? Get out of there. And so I'm going to have, from equation 2, reduces down to y equals 2x. Equation 3, z equals 3x. Now I can put those two in there. X plus 2y plus 3z is 6. So it's going to go into equation 4 now. So I'll put that in for y. I'll put that in for z. And I'd get x plus 2 times 2, 4x. 3 times 3, 9x is 6. And that's going to let me get what x is. All right. Any questions on the algebra here? So once again, you get these systems of nonlinear equations, and you just kind of got to run with them. Sometimes you'll get into a place where you thought, well, maybe I'll try something else. But you have to kind of keep the big picture in mind as you go through them. So how many x's we got all together here? 14 of them. So I got 14x is 6. So x would be 6/14, which is 3/7. Now I go back. Y is 2x. 2 times 3/7 is 6/7. Z is 3x. 3 times 3/7, which is 9/7. And we just have to check that we get a lambda out of this. Lambda would be x over the square root of x squared plus y squared plus z squared. And we just argued that the only time this would be undefined is if x, y, and z are the origin, which it's clearly not. So this is going to give me a number. All right, and that's all I need. There will be a lambda that goes along with this point. So the only critical point is 3/7, 6/7, 9/7. And if I want to know what the function at this point is, I got to go back to the original function and plug this in. You mean like here, Cole? Yeah, you could just say this will be, you just need to argue it's some kind of number, yeah. I think, though, the lambdas work out nicely. I'm just, it's just, we just need to make sure that there is a solution to it, yeah. Now, if you do a project, that could be a project. What did the lambdas mean in all these situations? But yeah, we just need to know that you get a number out of that the system is consistent. All right, so you go through 3√2 over √7 apparently. Yeah, if lambda isn't a number, then that means the system isn't consistent, which means that it's not a critical point then. So if you look back at the one we did yesterday, we did one yesterday where like we had a lambda, but we didn't get an x and y and go with it. So that was a case that didn't give us any solution. So that would sort of be the inverse of that. Yeah. Yep. Let's see what we get out of this. We should get a 7 down here. Right? And then this would be 3 squared plus 6 squared plus 9 squared. Which I guess I could take a 3 squared out of all of this, right? Did I do that right? So that would be 3 root, what? 5 and 3 root 14. Now it says minimize, so I guess that's the minimum. But how do we know it's the minimum? What's happening geometrically? So a lot of times with the method of Lagrange multipliers, when you go to argue, like in the book, homework, they just tell you find the maximum. It's like, all right, but what's actually going on here? Because this is actually a problem we've done before, back when we did vector stuff. Let's think about what this is. Our function f is calculating the distance from a point to the origin. And what's this constraint? What's the graph of this look like? This is a what? It's a plane, right? So here's what you can think about. What our f is doing is it's calculating the distance from the origin to a point x, y, z, and because of the constraint, that point's on the plane x plus 2y plus 3z is 6. So if we're minimizing the distance from the origin to a point on the plane, we're not only calculating the distance from a point to a plane, we're actually figuring out what point on the plane is that minimum distance. And if those kind of shenanigans sound familiar, they should. And I closed it, darn it. Let's take a trip down memory lane. No. Okay, that's too far back. That's not back far enough. No, that's vector valued stuff. Must have been take home 2. 6 weeks ago. Remember these kinds of problems? The cat is excited about this. Where did it go? I'm scrolling the wrong place. Calculate the distance. Now this is a different plane, but calculate the distance between a point and the plane. So this is calculate the distance between the origin and this plane. We can actually go through, and we have a formula to help us with that, involving dot products and normal vectors. And then this was one way to go about figuring out the point on the plane. All right. So back when we just had this set of tools, we had to go through this. And I think some of you did this, actually. This looked intimidating because there's a lot of letters going on. But when I actually went through the process, it wasn't too bad. So if you want a couple extra points on the next take home, you can go back to take home 2, get the equation of this plane, and then basically repeat this example with that plane. And not only will you get the distance, which was part of the take home you had to do, but you can now get that point as just a consequence of doing Lagrange's theorem, right? So once again, if you want, so for an extra 5 points, you want to go back to take home 2. And basically you get to do this bonus. But instead of doing it this way, you can use a more sophisticated tool, Lagrange multipliers. So you clear what the bonus is on that? So one of the things that tends to get lost in these classes is, like, as you move through and develop more techniques, you have more powerful tools. You can go back and revisit things that you've done earlier. Okay, so that'd be a little bonus there for you. Here it looks like this must have been one I'll have to go back and look at the notes, because we simplified here. This was simplified for some reason, and there's a reason I wrote it that way, but it's equivalent to what we had. All right, extensions to more than one constraint. Yeah, that's essentially what you're doing, Derek, to get the distance. But if your initial point is the origin, then your delta x is just going to be x minus 0. And so that would get you the distance, but then you actually want to figure out the location on the plane. Yeah. No, you got the right idea. Yes, I know. Ravine is very upset about extending to more than one constraint. All right, so once again, this would be a nice little project here to explain where this comes from. Because if you've got one constraint, great. Now we got 2 constraints. What happens is you introduce an additional Lagrange multiplier. So what you're saying is that the gradient of f lives in the plane determined by the gradient of g and the gradient of h. So you got the gradient of g and you got the gradient of h. And then the gradient of f is some multiple of this plus some multiple of that. So if I think about the vector stuff we did, so the gradient of f is some multiple of gradient h plus some multiple of the gradient of g. Why is that true? What's going on there? There's some, you can look at it from a linear algebra kind of a thing. The surfaces intersect to form a line. That's one way to think about it, yeah. Yep. But there's a nice little project there to dig a little deeper. So yeah, in this particular example, we want to optimize f of x, y, z equals x subject to z equals 4 minus x squared minus y squared and z equals y. So exactly what Zoran is saying here. If I look at these two constraints, we're looking at, we got two surfaces here. Okay. So if I fire up Desmos to help out here. And you might recognize these, sir. It depends on how much you've played around with Desmos, but this is going to be our classic paraboloid here that we've seen a few times. And this is the plane. There we go. So if I look at a point satisfying the first equation, that means that that point is on this paraboloid. If I look at a point satisfying the second equation, it means it's on this plane. So if we are on both, if we satisfy both equations, we're on both the paraboloid and the plane. And so you can see that's going to trace out a curve, right? A one-dimensional thing. And we want to optimize, that means find max and min of the function x. Sometimes this function is called the forgetful function. Because you're forgetting about y and z, you're just reading out the x coordinate. So if you think about what that means, is we're looking at, to be in the constraint here, to satisfy both constraints, you're on this curve of intersection, which GeoGebra does a nicer job showing you that, but GeoGebra is just too clunky now. I think GeoGebra tried to update after Desmos 3D came out, and now I just can't. It's just ridiculous to work with. So you'd be on this curve of intersection, right? Which looks like a what? If you had to guess the shape of this thing, the curve of intersection, what does it look like? Yeah, it looks like an ellipse, tilted circle, something like that. So if you're looking at optimizing x, you're basically forgetting about the y and z. You're looking for the points on here that have the biggest and smallest x value. So basically I'm just be looking down the x-axis here and seeing what those x values are, right? So we should be able to kind of see it if we do things carefully. So here's what we got to do. First off, we've got our objective function f. They just told us what it is. In order to identify the g and the h, we need to do the thing where we get all the letters on one side equal to a constant. So we've got z is 4 minus x squared minus y squared. I put all the letters together, I get this. Because once again, I want to look at this constraint as being the level surface of a function of three variables. So we could take our g to be this. And we got our z equals y. And there's a couple different ways we could get all the letters on one side there. So we could take our h of x, y, z to be z minus y. Okay. All right, so once again, you want to rewrite your constraints as a function equal a constant. And now we're off and running. So if I look at the component by component breakdown of this, right, I'm going to have fx is going to be lambda gx, lambda for Lagrange, plus mu hx, mu for multiplier. So fx, well, that's just 1, is going to be lambda gx, 2x, plus mu hx, but there's no x's there, so hx is just going to be what? 0. So no mu's there. So here I'm going to get 2 lambda x is 1, so that's going to be equation 1. Then I do fy is lambda gy plus mu hy. So that's lambda gy is 2y plus mu hy is minus 1. And this is all equal to fy. But what's fy? There's no y's in here, so fy is what? 0. So here I get 2 lambda y minus mu is 0. That'd be equation 2. And now I'm off to fz. Lambda gz plus mu hz. Once again, there's no z. So fz is 0. Lambda gz. So here's g. Gz is just what? And for that matter, hz is just what? Yeah, that's just lambda times 1 plus mu times 1. So this equation 3 gives us lambda plus mu equals 0. And then equation 4 is the constraint equation with the g in it. So equation 4 is just x squared plus y squared plus z is 4. And equation 5 is the equation that h, the constraint from h, z minus y is 0. All right? And now it just becomes a bunch of substitutions and eliminations. So if I look back at these equations that I've got, there's all kinds of things we can start doing. Like, for example, equation 2, I can figure out what mu is in terms of lambda and y. Equation 3, I can figure out what mu is in terms of lambda. Equation 5, I can get z equals y. So at this point, it's just really however you want to go about it. You're spoiled for choice here. So these two, we can plug these into the other equations. So let's do that. Let's plug this one. So we go back to equation 1. See, equation 1 had 2 lambda x is 1. So that's not going to change because I haven't done anything there. What's equation 2 going to look like? Equation 2 was 2 lambda y minus mu is 0, but I know that mu is minus lambda. So what would that? Oops. So instead of 2 lambda y minus mu is 0, I'd have 2 lambda y minus mu, but mu is minus lambda. is 0. So it'd be 2 lambda y plus lambda is 0. Equation 4, I would just sub in z as y. So I'd have x squared plus y squared plus z, which is y, equal 4. So now I've gone from 5 equations and 5 unknowns down to 3 equations and 3 unknowns. And then I can just say, okay, well, I pick one of these. Like I could pick this one here. Look at that equation 2. And I could factor out a lambda because I got stuff all set. And then I can look at 2 cases. So this is going to give me 2 cases. Case 1, lambda could be 0. What would case 2 be? Yeah, y be minus a half. Good. Oop, that's y. So run down case 1. Case 1, lambda is 0. So now I go back to these equations. So equation 1, if lambda is 0, well, we're done right away, right? Because if lambda is 0, then we're in trouble. Equation 1 would look like 0 equals 1. That can't happen. So that's out. You follow? It's just not consistent. So case 2, let's see if we get anything out of this one. Case 2, y is minus a half. That's not going to do anything for equation 1. Because equation 1 just has x and lambda in it. Equation 2 is where I got that from, so that's going to be fine. Let's look at what equation 3 has in store then. So we go back to equation 3. Mu was minus lambda. All right, so I guess that's... Does it have any meaning? I'm sure there's meaning if you extend things to functions of complex variables. That'd be a great question if you do extensions on this on your project. That'd be great. What would 4 look like? Well, here, this will give us what x is. Because if I know y is minus a half, I'd have x squared plus minus a half squared plus minus a half. That's all equal to 4. And then what was equation 5? Z equals y. So then z equals minus a half then. So in equation 5, I'll just sneak it in here. Z equals y. They give us z equals minus 1/2. That's x, y, and z. So now I can get what x is from here. So we got a couple minutes here. We should be able to finish this one off. So x squared plus a quarter minus a half is 4. So x squared minus a quarter is 4. So x would be 4 1/4, 17/4. And so you take your square roots. There you go. And now I just go back. I've got my y and my z. Those are my y's and my z's. So here's the same. And now I go back just to see, am I going to get a lambda out of this? Well, if I look at equation 1, it'll get me the lambda. Equation 1, I can go ahead and divide through by the 2x because the x isn't 0. So that'll give me a lambda for both of those cases. And then equation 3, I can get my mu, because that's going to be the opposite of whatever the lambda is. So once again, I'm going to get numbers for these two things. And that's all that I care about. That means I have a consistent system. All right, so that means my critical points are plus or minus root 17 over 2 minus a half minus a half. And if I look at f of this, I plug those in. If I look at f of the positive one, once again, f is just a forgetful function. It forgets about y and z. I'm going to get the positive 17 halves. And if I plug in the negative, I'll get the negative root 17 halves. So that must be the max, and that must be the min. And so when I fire up Desmos, I should be able to plug in those points, and those points should be the extreme values where those two surfaces intersect, at least extreme as far as the x is concerned. So any questions on solving the system? Is the thing that can get kind of tricky. So a lot of times you just got to follow your nose, kind of go after the stuff that looks easy to solve. But the key is organization. So especially when you get into different cases, you want to keep everything nice and organized. Not only for your benefit, but for mine. So I can kind of follow what you're doing. All right, let's finish this off here. Square root of 17 over 2 minus a half minus a half. See if that works out. Okay, and then negative of that. I think I can, let's see, can make these surfaces translucent. Translucent surfaces. All right, that works. I guess that's a little better. Let's make these points. I guess green's okay. Boom. Okay, there it is. All right, so here's the 2 points, and I look straight down the x-axis here. So first off, you can see that these points are on both surfaces. That means that they satisfy both constraints. You could algebraically check that these satisfy both constraints by plugging in x, y, and z to be these numbers. They're on the plane z equals y because they're the same. But then you plug it into the other one, x squared plus y squared plus z. That works out to be 4. So that shows that they satisfy both constraints. And sure enough, I look straight down the x-axis. Maybe I should do that from below. Might be able to see them better. Those are going to be the, well, maybe not. So if I look at the curve of intersection, these are the extents, the furthest x in both ways. So if you look at the curve of intersection, the x values are going to be smaller, oops, as I go in. So these are the furthest extents on that ellipse. Now if you wanted to, you could actually go in. Oh, no. You could actually, let's stop, that's making me dizzy. You can actually go in here and parameterize that surface of intersection. You could let y be t, so z would be t, and then you could actually solve for x if you wanted to. Or you could let y be like sine of t. This is probably better. Z would be sine of t. And then you would get x in terms of like cosine of t. You could actually parameterize that and then look at the x coordinate and find the max and min that way. So the thing about Calc 3 is we get a lot more tools to use to analyze these types of things. And then, as I mentioned, what does a Lagrange multiplier mean? This will get you started on that. So in some textbooks, this is how they do the method of Lagrange multipliers. But you can go through here, and this would be a nice start to a project. Okay, and then there you go. There's some problems to work on. Some of these problems are nice because they revisit problems in 15.7, and you can do them with Lagrange. So as I mentioned yesterday, tomorrow will be a work day. Feel free to tune in, hang out, work on the take-home. You got a nice bonus today. You can work on that as well. Go back and revisit some other things. If I don't see you, have a great rest of your week and a nice weekend.